Welcome to lecture number 13 for CIVE 360. And we're a little bit off schedule, but not much in that we have not taken the time to review for a little while. So why don't we go and take a few minutes to do that. So once again, I'm going to pose a question, and then I want you to just mentally think to see if you can answer it. All right, first off, what is the symbol that we use for the coefficient of thermal expansion? And if you need to, you can pause, that's fine, but I'm just going to give you a second or two to answer it. And that is alpha. What are the dimensions of the coefficient of thermal expansion? The answer to that is 1 over temperature, because remember it is strain per degree temperature change. What is the constitutive law for the total strain, including both mechanical and thermal effects for an axially loaded bar? So the one-dimensional constitutive or stress strain law, that's going to be the total strain, which remember is what we see and measure, is equal to the mechanical strain, that's sigma over E, stress divided by the modulus elasticity, plus the thermal strain or the free thermal strain, which is alpha times delta T. So that is the total strain is equal to mechanical strain plus the thermal strain. Then when we integrate that, we get the total displacement. So what is the total displacement including temperature effects? See if you can sketch that out. Hit pause if you need to. All right, I'm going to go and write it out. The total displacement then is going to be PL over AE, because remember, P over A is just the stress, plus alpha delta T L. So we just integrate the thermal strain over the length of the bar. What is our expression for the shear stress inside of a circular section? Tau is equal to T rho over J. What is our expression for the angle of twist for a circular section? The answer to that is theta is equal to TL over JG. And then finally, what is J? What is our definition for J? Again, hit pause if you need to. It's going to be pi over 32 times the outer diameter to the fourth minus the inner diameter to the fourth. What are the three primary tools of structural analysis or structural mechanics or solid mechanics? The first is statics. The second, stress strain. The third, compatibility. And remember that for the axially loaded bars, there are three types of SI. For torsion, there are only going to be two. If I have a section that is a composite, and it looks like this is material 1, this is material 2, and let's say that I say that G1 is greater than G2. G1 is greater than G2. So if I go from the center to the outermost point, what is the stress distribution? Let's blow this up. So if G1 is greater than G2, what does the stress distribution, tau, look like? Oops, I should say tau right here. Pardon me, that's as a function of the radius. Sorry about that. So G1, the core, is greater than that in the shell, and the answer is this. Then there is a drop down because of the mismatch, and it goes out like so. So that would be the shear stress distribution if G1 is greater than G2. Now notice, tau there is bigger than this one. So it is very possible for us in a composite to have a shear stress that's a maximum that's not at the outermost section of the entire section. Let's go ahead and write that up. Note, the maximum shear stress is not at rho max. That would occur if the value of G2 is greater than G1, but we've shown an example where that's not going to be the case, and you actually have that the shear stress inside is greater than the shear stress at the outermost radius. Of course, if it's hollow or solid, it is. Let's put that as a parenthetical. If solid, for hollow homogeneous, then tau max is going to be located at rho max. But if we do have a composite, then that's not necessarily going to be the case. So those are the formulas then that you should really kind of have committed to memory since our first exam. So make sure you're kind of keeping up with those and you're keeping your sticky note. Okay, so that's the end of a review. We took about 5 minutes to do that. And you should do this on your own if possible. The second type of torsion problem that we're going to look at is really kind of remarkable because it's amazing that we're going to be able to boil it down to a relatively simple formula. And this is called the torsion of hollow thin-walled sections. We'll underline that. That's our new topic. And this is a very common sort of structural mechanics problem. So there are basically two requirements. And they're listed in the title. One, the section is hollow. And two, it's made of something that has a thin wall. See, that and that. Kind of ridiculous. But it means it doesn't have to be a circle. It could look something like this, as long as it's got then a section that's going to be relatively thin. Now, I am going to give it some variability. Like so. In other words, this is small relative to the other fundamental dimension. So if this we just call B and that's T, what we're saying is that T has to be quite a bit less than the other dimensions of the problem. So an eggshell, if it were going under torsion, a Mountain Dew can that's been cut off at the ends, a paper towel roll, things like that. They have a thickness that's relatively small relative to their radius or their diameter. But T can vary. So let's put that as item number 3. T can vary, which is it's going to appear that's going to make this probably even more complicated, but it turns out that it won't. This is a really challenging problem if we were to take this up to the level that we would look at in a more advanced solid mechanics class. Let's just say, in reality, this is a tough problem. You end up having to solve a series of differential equations. It is not easy, and it takes quite a bit of theoretical background. In the sequel to this class, which is CIVE 560, we do this problem. And it's tough. It's kind of the ultimate problem that we do in that class that weaves together everything that we've studied up to that point. So it is not simple. But it's extremely interesting, and this is a very, as I mentioned, a very, very common engineering problem. So these sorts of sections are used all the time. Why is that? Well, because it turns out that if you do make your section hollow, it's extremely efficient. You have a small amount of material. And it turns out that it's quite strong. And it's also relatively stiff. So it's resistant to shear stress, and it's resistant to rotation. Now, we are only going to look at the strength aspect. We're only going to get an idea for what the shear stress is. The twist we actually save for CIVE 560. But we're going to go ahead and focus just on that stress calculation. So let's say our focus is finding tau is equal to something. We want an expression for the shear stress in this thin-walled hollow section. The first thing that we're going to consider is the following. Let's go back to the circle. So let's take a circular section, make it really thin-walled. Like so. Now I'll give it a little bit of thickness just so you can tell what the difference is going to be. Like so. Now what does the plot look like for this? We've already done this. We know that it's linear. So it's going to go like so. And then like so. So that is a shear stress distribution. So we've got a fairly small range for the numerical value of tau. So in this thin-walled section, we can see that it is linear across the thickness T. So remember, this is T. And this would be our, now it depends on where we put this, but I'll just call that rho to the inner wall. But we have said that rho to the inner wall is much, much bigger than T, or that T over rho is going to be very, very small. So the shear stress is linear across the thickness. This is the value of tau. So the shear stress varies linearly, but notice T doesn't change that much. So we'll say, but T is small. And so if we compare tau at rho sub I versus tau at rho sub I plus T, they're close. Clearly, this one's going to be bigger. That's larger because it is linear and we are increasing it a little bit. But if we're saying that T is small relative to the inner radius, that means that these guys are roughly the same. So here is our first assumption that we're going to make. We will assume, and it is an assumption, it's not quite true. It's not even true for the circle. But we are going to assume that tau across the thickness is constant. That is a big assumption, and it's one that is relatively accurate. It's not perfect, but it's quite good. And that simplification is really going to help us as we make our way through this. And we're done with part 1.